Good. Yeah. So as you can see, the title is Data-Driven Stochastic Optimization. And this first part is just about what is stochastic optimization? What do I mean by stochastic optimization? And I mean, broadly, stochastic optimization captures any optimization problems where you involve some kind of uncertainty captured by probability distributions. There are random variables involved. So big applications include things like operations. How do you, if you're running a warehouse, like you're a company like Amazon or something else, how do you store how much inventory to keep? Things like insurance, investments, like there are many, many broad applications. Every field of optimization often involves some kind of uncertainty. And whenever you have uncertainty, one very natural way to capture it is via some kind of random variables in probability distributions. Of course, I won't be talking about such broad horizon. Let me formalize things a little bit here in this talk or this week. So the way I'll think of stochastic optimization is it's basically some kind of an optimization problem where there are a bunch of random variables involved. I'll usually think of them as n independent random variables. So in classical optimization, like say, take a problem like you want to find a max weight matching in a graph. I give you a graph, you know all the edge weights, and you want to find the max weight matching. Now, what could be like a stochastic variant of it? Like the weight of every edge is a random variable. You don't know the realizations of these random variables. Maybe you know the distributions. So think of these xi's as capturing the weights of these edges. These are random variables drawn from some distributions. I'll usually assume independence. And in this first part of the lecture, I'll also assume that the distributions are given to me. But as you can imagine, like later, the major focus of the rest of this week would be more about the part where you don't know the distributions. I only have some kind of historical data. But to take it slow, in this part, we'll assume that the distributions are known to you. Given these distributions and some kind of problem constraints, maybe the constraints could be I want to find a matching in a graph. I want to find some kind of a path in a graph. It could be some other kind of, like we'll see maybe lots and lots of examples. It could be some kind of inventory management problem. It could be some kind of an auction theoretic problem. Given a bunch of such constraints, your goal is to find an algorithm to maximize or minimize your objective function in expectation. Good. So just to make sure the notation is clear, like alg is something that I'm trying to find. Alg is my algorithm. And x1 to xn are my random variables. So actually, recalling Roy's talk, so he was also using a similar notation. He was calling alg to be w. W was like whatever parameter, and there you had some distribution, and you were trying to evaluate the performance of your algorithm. The reason I've written it as x1 to xn rather than this, because rather than general x, is because you will often assume these are independent random variables, and a lot of the algorithms, especially for the data-driven aspect, will crucially use the fact that they will try to exploit the fact that these distributions are independent. So for general problems, for arbitrary correlated distributions, turns out often nothing can be done. There are very big hardness results. So yeah, but stochastic optimization is basically you have an optimization problem for which you want to find an algorithm solution and given some distributions. And like some simple examples these are broad areas. I'll get into more details, such as like auction design, some kind of resource allocation problems, inventory management. You can talk about problems like binary facility location, stochastic versions of that. You can talk about sequential testing. So these are like lots and lots of fields, lots and lots of applications. There are, again, depending on your background, I'm hoping like you've come across some of these problems before. And the high level question in classical stochastic optimization is, given all these distributions, how would I find an optimal algorithm or a near optimal algorithm in polynomial time? So as you can see, there's, in some sense, it's a fully optimization problem given these distributions. So I just want to find the optimal solution. Computation is the only bottleneck. If I give you infinite computation, then potentially, let's say, you can check out like every potential algorithm. You can test its performance because you know the distributions, and you can take the best of these algorithms. So the entire challenge is that how would I do it in polynomial time? But as you'll see later in this week, like another challenge would be that I don't even know the distributions upfront. I only have some data, historical data, and then things become even more complicated. Any questions? Yeah, feel free to interrupt me anytime during the talk. Yeah.
How do you assume the distributions are represented?
Yeah, so that's a good question. Like, how is the distribution even given to me as an input to an algorithm designer? So sometimes people assume explicit distributions in the sense that I can tell you like with 0.1 probability, this random variable is going to take this thing, with 0.2 probability, it's going to take. So then in some sense, when I say polytime, it would mean polynomial in the representation. Sometimes but maybe you're working with a continuous distribution. So then you might need some oracle of the kind, like, can I compute the expectation of this random variable? So yeah, that's a very good question. And I'm going to keep it intentionally vague because yeah, depending on the problem, yeah, I might want to change things.
So the algorithm is an input of the objective.
Yeah. So yeah, algorithm is basically, let's say I'm doing matching, stochastic matching, then a potential matching solution that I play, that is what I'm calling an algorithm. And an algorithm, or maybe a better notation would be an algorithmic solution.
It means that if I coded the algorithm one way, then.
So maybe algorithm is not the best notation here. What I mean by algorithm is more like a solution, a potential solution. So you have a class of solutions in which I'm going to play one of the algorithms. Good. So maybe I guess, yeah, as you're saying, like, let's maybe look at some concrete examples. So one of the simplest examples is maybe revenue maximization example, the simplest setting of single buyer, single item. So like here's a toy example, you have a carrot and a bunny wants to buy it. You as a producer of the carrot, you need to decide a price at which I'm going to sell this carrot to the rabbit. The bunny comes every day and its valuation is drawn from some distribution. So there's a single item. The valuation of this bunny for this carrot is a random variable from some known distribution D1. And the reason I have an index 1 is because sometimes you consider generalization of the problem where you have like multiple kinds of different potential buyers. But here there's a single buyer. And your goal is to maximize revenue. What kind of an auction can you run? You have to basically just set a price. So if I set a price P, the revenue I will make is precisely P is the money I make times the probability that the bunny buys the item at the current price, at this price P. So this is an optimization problem. I want to maximize over P my revenue. So this revenue, this is the expected value of the revenue for price P. Is this making sense? Like it's one of the simplest optimization problem. And again, like in this special case, you can even write like a closed form solution. But this is giving you an example of an optimization problem. And when I say an algorithm is basically, I meant here like playing a price. So your algorithm is making a decision what price to play. Good. So this is a simple one-dimensional problem, but there are generalizations of this for multiple buyers, as I'm calling. I'm not even going to define that problem very formally, because then I'll have to get into all the details of what does it mean to be an auction, what does it mean to be a truthful auction. But these are like very deep concepts. For instance, like Meyerson, who's credited to be giving the first solution, the optimal solution for this problem. When you have multiple buyers and a single item to sell, he gave the optimal auction back in the 80s, and he like won like a Nobel Prize in economics. And one of the reasons was precisely understanding auctions better. So these things can get much deeper. What I meant to say is like already this simple looking problem, as soon as you go to higher dimensions or like multiple buyers, this becomes pretty complicated. And fully known distributions, already the problem is very complicated. Any questions? So I'll be mentioning like many examples, like more to keep things concrete. So here's the second problem. This is the so-called optimal shopping, what I'm calling it, but it's pretty much the profit inequality problem that Paul talked about. So again, I'm assuming it would be easy for you to digest because, yeah. So what's the problem? Just to recap, it's basically you have n random variables. These are like your n boxes. You're going to see their realizations one by one. So you first see the realization of x1, then x2, then x3. You know their distributions. Upfront, you don't know the realizations. Your goal is to select. As soon as you see the realization, you have to decide, are you going to take this or not? You can take at most one of them, and your goal is to maximize the value. So people also call it the stopping problem, optimal stopping, because you need to decide when to stop. When do I take this random variable? Good. And I mean, yeah, okay, one can run example, but I guess I'll go over this quickly because you already saw this a lot in the morning. And there are, so as maybe Paul also talked about, that the optimal solution is given by a reverse dynamic program. So this is the optimal solution. Like you basically start off with the last random variable and go behind. I mean, I'll talk about this more in detail. So one thing that will be different from profit inequality versus this is the setup is the same. The difference is the benchmark. Paul was often comparing his solution to the expected max, the expected hindsight optimum of all these random variables, which is in general not achievable. You can at best hope to get like a 2 approximation to it. Whereas our benchmark here is in some sense the optimal solution, which is given by this dynamic program. So in some sense, you can find the optimum solution. So the reason we'll focus more on this optimal solution, because this is like very broadly well-defined for all stochastic problems. Whereas for most stochastic problems, if you compare yourself to the expected hindsight optimum, then usually you cannot get any guarantees. So this is like a much broader, yeah. So I'm going to use optimal stopping more as like, again, an example, as a running example. Good. So, and again, this can be generalized to many, many things, something like called resource allocation, online algorithms. Yeah, and Paul also has been talking a lot about this. Any questions? So again, like what I'm saying, I guess the point was, this is again can be thought of as a stochastic optimization problem. I give you all these random variables up front. I give you the arrival order. Your goal is to come up with a policy that maximizes the value in expectation. It's just a stochastic optimization problem. Here's another problem called as Pandora's box. So what's the setup? Think of it as follows, like maybe you're running a university or a department. You want to hire a candidate. You receive all the applicants. There are n potential applicants. Based on their CVs and the letters of recommendation and whatever, you have some distribution on how valuable they are, like how much competent each candidate is. But upfront, you don't know the exact value. I mean, you have some distributions on each candidate now, but you don't know the realization. You can find out the exact realization of any random variable of any candidate by scheduling an interview, but that's going to incur like a bunch of cost. Like you have to reserve a bunch of places, find a lot of people to interview them and so on. So a bit more formally, you have n distributions. Xi is the random variable, which is drawn from some distribution di, value of the ith candidate. You can find out this realization by paying some cost Ci. That's the cost to interview. And you just have one slot. So the goal is basically you want to interview a bunch of these candidates. Amongst the candidates you interview, you are going to hire the best one. You want to maximize your value minus the cost. So more formally, so you want to interview it as the subset of candidates that you interview. You want to maximize among I in the interviewed, Xi, minus some of the interviewing cost. So notice that the cost that you're paying is summed up over all the candidates, but the value you're getting is just the max, because you only have one position. There are, of course, like all these problems, by the way, I'm defining that you can define massive generalizations of these problems. When you're hiring multiple candidates, you could even define like matching versions of this problem. I give you a graph. Each candidate is basically an edge in a graph, and you can find the weight of the edge by paying some cost. So yeah, but let's not get there. So the question is, again, if I want to maximize this objective, this is some random variable. I want to maximize this objective in expectation. How do I come up with an algorithm? An algorithm, what it means is some kind of a policy here. Basically, I interview a candidate. Depending on how good the candidate turns out, maybe I'll just immediately stop and hire them, or maybe I continue interviewing more. So an algorithm here is some kind of a adaptive decision tree policy and so on. And again, this like problem has been deeply studied. Like here's like a small example, like you have these, again, n distributions. Maybe I decide to open this third candidate interview. They turned out to have value 2. Maybe I'll continue, maybe I'll not. So like I'll go over this fast. But basically, yeah, I mean, like in this example, like I paid some prices. My total value was 6. I opened all like 3 of the boxes and I got like a price of 3. So, but again, this is like an old problem from econ. It was studied already by economist Weitzman in the 70s. Turned out you can actually, it looks like a very complicated problem. There's actually a simple polynomial time algorithm for this problem. Yeah, so we'll get to it in a bit. So the point was that, okay, there are all these like many different kinds of stochastic optimization problems. So how do we, in general, define, first of all, the optimum solution? So for any of these stochastic optimization problems. So one way of thinking of these stochastic optimization problems is you can think of it as a massive Markov decision process or a massive MDP. So actually, how many of you have seen MDPs before? Okay, most of you have. It doesn't matter too much. But just that, like, yeah, if I am giving intuition, like the intuition may or may not make sense accordingly. But yeah, so I can think of an MDP here, like let's say Pandora's box. A state would represent something like, here is a subset of candidates I have already interviewed and their valuations have turned out to be this much. So that's my state. Based on this state, my action could be, this is the next candidate I'm going to interview. Depending on what action I take, I'm going to get some potential value. I'm going to transition to a different state. So you can think of any such problem, any of these stochastic optimization problems that I'm talking of as an MDP. The question is, I want to come up with an algorithm or policy that maximizes my value in expectation. The challenge naturally becomes here in all of these problems is, if you write it as an MDP, usually the state space will be exponential. So you can't really hope to solve like a dynamic program and solve it in polynomial time. So unless there's something nice, unless you understand the structure of the problem better, so you need to go deeper to come up with a nice algorithm. And that's why like this field of stochastic optimization is extremely huge, because, and these are like very important problems. So people from different communities have come up with different kinds of techniques to solve these stochastic optimization problems, even if I give you the entire distribution upfront. Like in the end, it's just solving an MDP. The question is, it's a massive MDP, like how do you solve it? Even if I tell you the entire distribution upfront. And as you're saying, like this week, things will become even more complicated, because now even I won't even give you the distributions. I'll only give you some historical data from these distributions. Does this make sense? Good. Yeah. So you can think of this as an MDP. Sometimes I'll also actually think of this as some kind of a decision tree, because for most of our stochastic problems, it will be of the kind that you will never go back to a state ever. Like once I've interviewed a candidate, I've now seen the realization of this candidate. There's no way I can like perform a sequence of other actions and then come to a situation where like this candidate has somehow refreshed. So because there are no cycles in some sense, it's a DAG. Or even like you can think of it, often think of as some kind of a decision tree. You start at the root node, you take some decision depending on the realization, you go like in one of the subtrees and proceed accordingly. Yeah. So, but as I was saying, like the main point here is that the bottleneck is computation in traditional stochastic optimization, because I've given you all the distributions and you want a polynomial time algorithm. And like, yeah, we have talked about these three problems, like the revenue maximization, where I was just selling a single item to maximize my revenue, the optimal shopping problem, the so-called profit inequality problem, which you can solve optimally using dynamic program. And Pandora's box is the third problem that I talked about, which was like hiring a candidate. And a priori, if I give you the stochastic problem, it's not at all clear, if you've not seen this problem before, that there is a simple solution. Like, is there a polynomial time algorithm? It seems like a pretty complicated problem. Like, depending on how first few candidates turn out, it's not at all clear which are the next candidate I should interview. Yeah, so I've written it as like an arbitrary decision tree potential. Good. And we'll get to again like later about unknown distributions. Good. So, but okay, these are just three problems I mentioned, like revenue maximization, which can be generalized to auction design, optimal stopping, which generalizes to online resource allocation, Pandora's box generalizes to things called stochastic probing problems. There are many, many other things like inventory management, something called as news vendor problem is one of their classical problems, which we'll talk about later. Stochastic knapsack, matching, submodular cover, sequential testing. I mean, there are lots and lots of problems, lots of books written on these things. Yeah, so all I wanted to say is like, okay, stochastic optimization is a very broad field of interest. And already if I tell you everything about the distributions, it's a non-trivial challenge to solve this problem. Good. So, but now we want to, and the question is, how do we find a polynomial time algorithm to maximize my objective? You could have also written as like minimizing my objective and like negative of the objective. So for the rest of this part, like lecture one, we'll basically focus on some techniques, standard techniques that people use in classical stochastic optimization to solve some of these problems. Like when I give you the entire distributions upfront. Any questions? Yeah, by the way, all these slides are also available on the link. I think Kevin has already put it up on the website. So yeah, in case you're interested. There are also some exercise problems there if you want to attempt. And yeah, feel free to see me during lunch break, dinner, or any of these times, like, or even during the lecture to ask any questions if you have. Cool. Okay. So as I was saying, like now we'll get into some of the techniques how to solve some of these stochastic optimization problems. So like we'll start off with some simple techniques and make it more and more complicated. So one of the simplest techniques is just some kind of a closed form solution. Okay, so some simple stochastic optimization problems, we can actually just solve the optimum solution, especially stochastic optimization problems that involve just like a single random variable. So simplest example is this revenue maximization problems. You were selling a single item to a single buyer. And if you recall, like the objective function I was trying to maximize over P is this P times 1 minus F of P. Capital F here is the CDF. So 1 minus F is precisely the probability that the random buyer's valuation is above P. So the item is basically going to sell. And of course, how the way you will do it is you'll set the derivative to 0. So you'll basically set some kind of a solution equation of this kind. This equals 0, and you can take its inverse and so on. Yeah, so that's like an example of a problem where you can get a closed form solution. For those of you who know more about auction theory, this is the same thing as something called setting the virtual valuation to 0. But yeah, let me not get there. This is more like how to extend these things. Yeah, for Meyerson setting where you had like multiple bidders fighting for a single item. Let me give another example, the so-called news vendor problem. So here's another classical stochastic optimization problem studied in the field of inventory management. So the setup here is the following. You're basically trying to produce some item, some good, but to produce more and more copies of an item, it incurs you more cost. You first produce a bunch of items, like I guess I'm calling it K, and then some random demand will come. The demand could be higher than K, could be lower than K. You are trying to maximize your revenue. So more formally, there's some sale price, some production cost, and some demand distribution. You need to decide an inventory, K, so that you're maximizing your value minus your cost. So what is my cost? Cost is literally K is if K items I produce, I'm going to pay C times K. And my revenue will be my sale price times min of K comma D. So if the demand is less than my inventory, then I guess min like will be the demand. If my demand is more than the inventory, then I'll basically get K. K is how much I produce. And so the goal is to maximize this quantity. And this is called the so-called news vendor problem. Again, it's like a very old problem in inventory management. There are generalizations and all as well. And again, the way you can solve it is just set the derivative to 0. Turns out you can compute the optimum solution. Any questions? Yeah, again, like none of these examples in particular is important. I'm happy to chat more about them. But I mean, yeah, I'm using more of them as motivating examples, but they lead to like, yeah, different areas. Good. So, but the problem with usually this closed form solutions is usually it's not possible when you are solving a stochastic optimization problem involving multiple distributions, multiple random variables. So for very simple settings, you can do it. In higher dimensions, things don't usually scale well. But for simple problems and like some classical problems, this approach does succeed. And whenever it does succeed, that's great. Good. Okay, so another approach is dynamic programming. Like as I was saying, like you can think of the optimal solution as some kind of a decision tree. So a natural approach would be you start off at like the leaves of this tree, decision tree, what is the expected value, and try to apply some kind of dynamic program, like from leaf up to the root. And usually like the running time of these algorithms, it would be like roughly like the linear in the size of the tree. So whenever it works, it's great. But often the problem would be that the size of the decision tree would be exponential because you're in higher dimensions. And usually the dynamic programming approach again will not work. There are exceptions. For instance, this profit inequality or the optimal shopping problem that Paul already talked about. The problem where you had these n distributions, you had to decide when to stop and take the random variable to maximize my value. Here, dynamic program actually works because you can think of it like literally start from the last random variable, which I'll always take, and I'll take I'll take the I plus ith one if its realization is more than the expected value I expect in the future. So the approach is that you, using dynamic program, calculate how much in expectation value I'll get in the future. So that we call that VI. And then I'll basically take the current value, random variable, if its realization is more than the expected value in the future. And you can show this is the optimal, which is basically can be computed using dynamic program. Does that make sense? Yeah. So again, like as I was saying, this dynamic program is a nice approach. It's very generic. It works for any of these MDP or any of these stochastic problems. The challenge is usually that the state space blows up exponentially very fast. And so unless there's something nice happening for your stochastic problem, this approach does not generalize. Like for instance, like this is something I think again Paul mentioned briefly about, like even if I talk to you about like a slight variant of this problem, the so-called free order optimal stopping problem or free order profit inequality problem, where again I give you these n distributions, but I allow you to choose the sequence. So the sequence is not given upfront. You can say like, okay, first tell me the value of the fifth random variable. Depending on its realization, then I can either immediately take it, but if I reject it, I can tell you now, tell me the value of the seventh random variable, then the second random variable. Like I can choose the order. So that's called as the free order problem. And already dynamic programming won't work. Like the state space will blow up exponentially. So the approach is also like not very robust. This, like, although the fact that optimal stopping you could do in polynomial time, a slight variant of the problem, still like a variant sounding which is like slightly different, already it becomes, actually there are reasons. In fact, this optimal stopping with free order problem is known to be NP hard. So in some sense, you cannot actually hope to find in polynomial time the optimum solution. So yeah, I mean, in general, stochastic optimization problems can be pretty hard, even if I know the distributions. And yeah, I mean, and then like, okay, if it's NP hard, then maybe you'll try to design an approximation algorithm and so on. Okay. So one approach that is again very powerful is this third technique called linear programming. Again, I'm assuming many of you probably seen some linear programming, at least in the non-stochastic context, like say classical NP hard problems like traveling salesman problem and so on. We can use linear programming based approaches or other approaches to design approximation algorithms. And you can actually do similar kind of techniques even for stochastic optimization problems. So for instance, like if I talk to you about like optimal stopping for the free order problem, like what's the approach via linear programming is basically I'm going to write some kind of an LP relaxation of the problem. And then I'm going to somehow round it to obtain from fractional to an integral solution. Usually, like these things, usually the LP relaxation, it's a relaxation. It doesn't capture the exact problem, but it captures the problem up to some approximation factors like a constant factor 2 or so on. Like the factor will depend on the problem. And yeah, so you can apply a similar approach even for problems such as optimal stopping. This problem, like to give you an example, maybe for simplicity, let's say your random distributions are very simple. Like it's some kind of a weighted Bernoulli distribution. So ith random variable xi is vi with some probability pi, and it's zero otherwise. So you can define generalizations of it when you have more complicated distributions. So in this simple case where your xi represents, like xi equals vi with some probability pi and zero otherwise, I can write a simple linear programming capturing something like the expected max of these random variables. It would be something like maximize summation over I xi vi. Xi roughly denotes the probability that ith random variable is the maximum, small xi. And you'll have constraints something like summation xi less than equal to 1. Each xi is between 0 and pi, because pi is the probability that it's taking value vi at most. And you can solve this LP. It's not exactly the original problem, but you can prove via simple rounding techniques that it captures the optimum up to some constant factor. So this is like an LP-based approach. And you can, for instance, like what Paul talked about, profit inequalities, you can also prove that via this LP-based approach that you can get the same factor to approximation. Yeah.
What will be the algorithm?
Good. So I mean, you mean the rounding algorithm, like, so I did not, yeah, exactly clarify here, but
So after the rounding, what is the algorithm? Like profit inequality, what is the algorithm? Like when do we stop?
yeah, so the algorithm would be of the following kind. Solve this LP relaxation. Okay, you'll get some fractional variables. Let's say x1 is 0.1, x2 is 0.3, and so on. Now, one algorithm that works is of the following kind. Whatever xi stars you get, maybe scale down each by factor 2, and now basically just work greedily. So in some sense, or alternatively think of it like every ith random variable, with half probability, I'm going to just skip it. I'm not going to take it. Otherwise, I'm going to take it if its value is in the top xi quant. So that can be shown to give like a constant approximation. That will give you like a factor 4. There are variants of it that can even get you factor 2. That's an example. This is the rounding part. I'm not going into the details, yeah, because again, like it's very problem specific. So here's one thing, like, I mean, in this tutorial, like, I mean, I could easily get into specifics of a problem. I'm trying to keep it more and more general. But yeah, but we'll go into some details as well. Was there any other question? Okay, good. So this is an LP-based approach. Again, that can be very broadly applied to lots and lots of stochastic problems. The advantage of LP-based approaches, usually it scales even with a higher number of random variables. And it's usually quite robust as well to variants of the problems. Like this is one of the biggest advantages of linear programming and even integer programming, especially in practice, is that like it's easy to capture constraints. I mean, if another kind of constraints comes, you just write it in the relaxation. I mean, at least it's one thing to start off with. And often it works pretty well as well. So it's nice. The downside of this approach is it often usually gives you just an approximation algorithm. And maybe rounding is also not necessarily clear, like how to come up with a rounding algorithm. So it is not good to get the optimum solution. But okay, maybe if the problem is NP hard, then we don't even expect to get the optimum solution. But even for problems which have an optimum solution, like polytime optimum solution, it's not obvious how to apply this LP approach. But this is like, again, a very powerful and generic approach that can be applied to many, many stochastic problems. Any questions? Yeah. So finally, I'll talk about like one more approach, the so-called index-based approach. This is for problems like Pandora's box. So this is again like a very generic technique to solve many kinds of stochastic optimization problems. Things like some of you might have heard of things called Gittin's index. So basically, it turns out like the reason we are able to solve Pandora's box problems is because it can be written as some kind of a problem where you can apply basically Gittin's index theorem. But okay, maybe getting into the more specifics. So this is another approach to solve a bunch of stochastic optimization problems. So maybe let me say the techniques tailored to the interviewing problem, the Pandora's box problem. So recall the problem is you have n potential candidates. Each candidate has some distribution. You can find out their realization by paying some cost. Goal is to maximize the value minus the interviewing cost. I want to come up with a policy for this. A priori, it seems like a complicated problem, and it's not clear how you would give the optimum solution. Turns out the optimum solution that was given by Weitzman is an index-based policy. So what do I mean by index-based policy? An index-based policy means the following. You have these random variables like these candidates. In some sense, based on the distribution of each random variable and the cost of maybe interviewing it, I'm going to assign some scalar value to this candidate. So each random variable, in some sense, originally it's a random variable, I'm going to replace it by a single scalar number. That scalar number is going to be called the index. And then my algorithm would be of the following kind. I'm going to interview these candidates in decreasing order of this scalar number, along with some stopping rule, which we'll get to. So usually index-based policies are very nice because they are saying that you don't really have to think of like arbitrary decision trees or arbitrary MDP solutions and so on. It says that just focus your attention to a very restricted class of algorithms, which basically upfront have replaced all these kind of random variables and so on with some scalars, and then you are running some simple like greedy-ish solution on them. So that's what I mean by an index-based policy. Turns out for this problem called Pandora's box, and even like more general, like a lot of stochastic optimization problems, this class of policies, index-based policies, actually capture the optimum for large class of them. Any questions? Yeah, so the next slide, I mean, I'm going to go into more details about like how exactly Weitzman's problem works. It's somewhat optional. Yeah, so in case you doze out, like it's fine. It's not going to be important for the future. But I wanted to cover up like some non-trivial techniques as well, how people go about solving some of these stochastic optimization problems. So yeah, question.
Very just a thought question for them, for the Pandora box. Does the person we want to hire, it makes it a difference if we do not have to interview it?
Yeah. So that's a great question. So actually, yeah, there's a variant of the problem. So in the current version, the classical one, you cannot hire a candidate without interviewing. There's another variant it's called usually Pandora's box with like non-obligatory inspection, where you're allowed to hire a candidate without interviewing them. and basically getting the expected value of that random variable at zero cost. So that's allowed variant. Turns out this Weitzman index policy is no longer going to be the optimum, but you can design something like this to get like a 2 approximation or like even something better than 2. Yeah, so I think 4/5 is what you can get, 4/5 approximation. Yeah, so yeah, exactly. Like, so there are like many of these variants of the problems, and they sound minor variants, but yeah, the optimum structure can change dramatically after. Any other question? Good. Yeah, but in the current variant, yeah, you have to interview a candidate before you can hire them. So good. So what's the policy? Now let me go. Maybe let's do okay, I have like 5-ish minutes. Let's do maybe an example. So suppose you have a very simple case. Suppose you have 1,000 IID random variables, 1,000 candidates. Each candidate has value like with very small probability, 0.01. They take a value of 200. Otherwise, they are 0. Think of it like either they pass the interview bar or they don't pass. If they pass, they have a value of 200. Otherwise, the value is 0. And to interview a candidate, it costs you like 1 in whichever unit, like, yeah, like $1,000 or whatever. So the question is, okay, what policy would I take in this special case? So here I'm saying it's like a simple, trivial solution. Because all the candidates look, they're identical, it doesn't matter. You basically start interviewing them. So the first question is, would I interview any candidate, or it makes sense for me to like just walk away with value 0? Yes. So yeah. So we would interview because the expected value of a candidate, a single candidate, currently we have 0 in hand, is basically 200 times 0.01, 0.001. So which is 2, which is more than the cost. The cost is like 1. So it makes sense to interview a candidate upfront. So basically the optimum algorithm would be of the kind, I interview the first candidate. If it's 200, then I immediately stop, because there's no point in interviewing any other candidate, because every other candidate's value, even if they pass the interview, will be exactly the same 200. On the other hand, if they fail, then I'm going to interview the second candidate, the third candidate, and so on. So you can argue that the optimum expected optimum will be roughly 100. But this does tell us like that what's the stopping rule for our algorithm? Like suppose we reach a situation where we have now, even if it's not identical distributions, I have already interviewed a subset of candidates, and I need to decide, should I interview any other candidate, or am I done? So there's a simple test for it, because you've already interviewed a subset of candidates. You know which is the best candidate right now. For every remaining candidate, compute the expected additional value you would get. So if you already have some current value in hand, the expected value you would get from any other, like from ith candidate, is expected of xi minus current, the non-negative part, like max of this comma 0. If this is greater than the cost, then it makes sense to interview this candidate. If this is less than the cost for every remaining candidate, then you should stop. So that's the stopping rule. Does this make sense? So what I'm saying is, the stopping rule is easy. Like if you already have a value in hand and every remaining candidate's expected marginal value is small, then you should just stop. But if what's not clear is if there are multiple good-looking candidates, in the sense that multiple candidates who have good expected value compared to their cost, then which of them should I interview first? That's the remaining part, and that's what this Gittins index will tell us, the index. Good. So turns out if you run just like some kind of a greedy-ish algorithm, like if I have like multiple good candidates, potential good candidates, which one should I interview first? One naive approach would be I just look at the difference of expected marginal value minus the cost. Turns out if you run the greedy approach on this, that was a bad idea. There are simple solutions. Simple example, like in this example, if I just add like one more candidate who has a deterministic value of 200, you can show that greedy fails like very badly. Instead, what Weitzman showed is that the right solution is something called as Weitzman's index. Now, it's the solution. So I'm assigning a scalar value to every candidate. So the scalar value I assign to the ith candidate is called tau I. So it's the solution to the following equation. Expected max of xi minus tau I, the non-negative part, when this becomes CI. CI is the cost of interviewing this candidate. So another way of thinking of this is the following. You have some distribution of this random variable. I want to come up with a curve such that the expected value above this, like this bar, this partition, is precisely the cost. So I want to replace for each random variable, each candidate, I want to come up with this index, this boundary. And then I'm basically going to just run the greedy algorithm based on these decreasing in boundaries. So that is the Weizmann's optimal solution. Is the algorithm making sense? I'm happy to take questions. Yeah. Yeah, it doesn't. So the index is, so one of the benefits is precisely this index doesn't care about, first of all, any other random variable as well. It just cares about, yeah. So the only thing that would matter on the past is this stopping rule. Because if I have interviewed somebody in the past, and maybe the current best candidate from the past is already very high, then this marginal value will be low. So I might want to not even interview this candidate. So yeah, that's the only sense in which it matters. But beyond that, it doesn't matter. So this is the policy. And okay, I'm going to skip the proof, but the proof is not that difficult. Roughly, the idea is that you think of, turns out you can define some kind of a mapping. The original world is you get some value xi of interviewing the candidate, and ci is the cost that you pay. Imagine an alternate world where there are no costs, but you get the smaller value yi, where yi is the min of xi comma tau i. So again, going back to maybe this picture, in the original world, you get some value xi, but then you have to pay some cost of interviewing ci. Turns out you can replace this random variable with a different random variable where you'd never get any value above this. Think of it some kind of an insurance. So it's the cost of insurance. So you replace the original distribution by a cropped distribution, which is capped here. And in this world, you don't have any cost to pay. And this is what I'm calling yi random variable, which is min of xi comma tau i. And you can show like some lemmas that algorithm's value is expected max of yi, and opt is also at most expected max of yi. So hence your algorithm is basically equal to opt. So this is the optimal solution. So, I mean, yeah, the slides will be available. So, I mean, yeah, you can check out the details. It's pretty short proof, like 4 or 5 lines. The original proofs were much more complicated, but now people have discovered much shorter proofs. And as I was saying, like this can be generalized. Actually, you can prove this result also via something called as Gittin's index theorem, if you've seen. It's a very special case. Yeah. So again, okay, the details were not so important. Here's the main takeaway from this part of the talk is, what is this field of stochastic optimization problem? It's basically, I want to say, like I've given you a bunch of distributions. The crucial assumption we'll make, these are mostly going to be discrete optimization problems, discrete stochastic optimization problems that I'll talk about, that I'll assume that these are some independent distributions. You want to come up with an algorithm or a solution which maximizes or minimizes your objective value. This captures many, many fundamental problems in many, many fields. There are many, many techniques that are known, like starting from very simple solutions, such as like closed form solution, where you set the derivative to 0, or like dynamic program based. But then there are more non-trivial approaches via linear programming and these index-based policies. So this is a very big field, and like lots and lots of books. But the rest of the week will basically focus on what if these distributions are not known to you and you only have some kind of historical data. So then what can we do about these problems? Be happy to take questions. Thank you. Okay, yeah, take a break maybe. 10 minutes.